Okay, so the plan for today is to just continue with chapter 6, continuous probability distributions, and make our way to the normal distribution. I'm going to pop a PDF in chat. So this is the standard normal distribution. This will be posted on Blackboard as well. And of course, it's in your book, and you can find it there as well. So the normal table that we'll use today is posted in chat as a PDF just to make it easier for you to access, but you can find it in the book. One slight note on this, if you Google normal distribution table, you might find a table that, they're all accurate. They all have essentially the same information on them, but the information is presented in different ways often. So I would recommend planning to use the one that we're using, just because that way it'll look familiar to you and you can kind of follow along with everything. There are different ways to present the same information in this table. So if you grab one off the internet, it might look quite different. Even though it's the same information, it might be presented differently. Okay, the quote of the day today is from Peter Arve, co-founder of Prezi. And I was talking with a friend over the weekend, and we were kind of talking about this. They're planning on going on a kind of going up to the mountains in a couple weekends and just like disconnecting from everything. And it made me think of this quote. The concept of always being reachable makes us present nowhere. Or I kind of like to think of it as like the concept of being reachable everywhere makes us present nowhere, right? We have these wonderful devices these days that that connect us to everything, and we can find essentially any information we want at a couple clicks of a button. But that tends to conflict with our ability to be present with the folks that we're sitting around the table with, at a specific moment. So, and especially if you have one of those smartwatches, I haven't gone and gotten one of those yet because I think I would be even worse than I already am with my always being on my phone. Just every time that it would pop up, I'd be like addicted to looking at the thing. But yeah, it's something to keep in mind. And also with our spring break coming up in a few weeks, something to think about there too. Maybe taking some time to kind of disconnect a little bit, to just be present with the folks that are around you, and and kind of a week where there's not a lot of projects or emails or homework or anything like that, flying back and forth. Okay, so that's the thought for today. So last time we introduced the idea of continuous probability distributions. It's a bit of a strange idea, so I would like to kind of do a really quick crash course to go back through that development. We're not going to develop it completely, so if you missed last class, take a look back at that class for a more thorough treatment. But this is more just a recap or a reminder for the folks who were here last class. So which hopefully was everybody. I kind of said that a bit strange, I suppose. But so we think back to discrete probability distributions in chapter 5. And the idea was we had a set of outcomes where it made sense to ask for this outcome, what is the next possible outcome? So like a die roll, you could roll a 2. What's the next possible outcome of 3? What's the next possible 4? And so on. And each of those had associated with it a probability. We thought of the outcomes being like locations and the probabilities being like masses, like mass in the sense of like a weight, a physical object, and the expected value being like the center of mass of this set of masses at these certain locations. And then we kind of, had the idea where we had a continuous variable where a question like what's the next allowable outcome doesn't make as much sense, right? If we're thinking of, say, heights, somebody could be 6 feet tall, or they could be 6 feet and 0.1 inches tall, or 6 feet and 0.001 inches tall, or 6 feet and 0.00001 inches tall. There's no real concept of a next possible height. If one outcome is 6 feet tall, what's the next possible height? Not really a clear idea of what that even means. So for continuous variables, we need to have a different approach. We can't just take this approach of kind of enumerating outcomes along with their probabilities. And what we said is we would take this continuous variable and kind of think of breaking up its range into some different bins, like a grouped frequency distribution. And then we might think of splitting those bins. Maybe the bins are of width 1. We could split them in half and make twice as many bins that are half as wide. And we could do that again and again and again. And we approach something that looks like a continuous distribution. And these have some strange properties, at least strange at face value. These distributions are represented graphically by graphs of probability density. And of course, that graph can be associated with an algebraic function. So they're represented either as an algebraic function or as a graph, not really so much as a table like we have up here. And we call these probability density functions, or PDFs. As opposed to up here, we call this is really a function. It's taking an input like x1 and associating it with an output, probability of x1. We call that a probability mass function rather than a probability density function. Since our graph of a PDF corresponds to density, we need to accumulate density. This is a linear density, a one-dimensional density. We need to accumulate density over distance in a sense, or length in a sense, to achieve probability. So probabilities correspond to areas under the PDF. And so just as a little example, if our PDF looks like this, we would call this little f of x. Little f in probability theory always refers to a PDF. We want to accumulate this density. I cannot draw straight lines today. My lines are all ski-wad. I need to accumulate this probability density over a linear distance. And that area that's beneath the curve, the PDF, above the horizontal axis, in between these two bits here, that's a probability. So probabilities are represented by areas. So for instance, asking in a continuous variable setting, what's the probability that somebody is exactly 6 feet tall? That probability would be 0. Because if my event is simply being 6 feet tall, that's just a straight line that has no width, it has no area, it has 0 probability. So kind of the more sensible or the more interesting types of events are events that are intervals. What's the probability somebody's between 5'11" and 6'1"? Well, that's probably going to be a positive number. That's going to be an interesting probability. So we can ask questions like, what's the probability somebody's approximately 6 feet tall? If we phrase to say something like this, and that would be probably the type of event that we most often want to talk about. It's not wrong to ask, to have an event that somebody's exactly 6 feet tall and to ask what's its probability. The probability is just always 0, so it's not very interesting. We also noted last time that we're not going to be in the continuous world, we're not going to be all that careful about strict versus non-strict inequalities because of that property. Because probability x equals a is 0, probability x equals b is 0, we don't really have to worry about the strictness or non-strictness of the inequalities when we're in the continuous world, when we're in chapter 6. When we're in chapter 5, we have to be very cognizant and careful about that, right? The probability of rolling a fair six-sided die and getting a number strictly less than 4 or less than or equal to 4, those are two very different probabilities. But in the continuous world, we don't have to be nearly as careful there. So if I have some function, some random f of x that I write down, what are the requirements for it to be a PDF? Not just every function can be a PDF. It has to meet these two requirements. It has to be non-negative. Otherwise, we might accumulate some density over a certain distance and get a negative area. What does it mean to have a negative probability? We know probability should be between 0 and 1. So the PDF has to be non-negative. and the total area has to be 1. Basically the same constraint on these probabilities up here, that they had to be non-negative and that they had to sum to 1. Okay, so we have the first distribution we had talked about, the uniform distribution. We can say that x is uniform on the interval a to b. And what we mean by that is that our PDF is a constant, in this case 1 over b minus a, to make the area turn out to be 1 on the interval a to b and 0 otherwise. So we can think of our PDF as looking like this. Here's A, here's B. Maybe I'll draw it in green. Maybe I'll draw it in red so we can see it a little bit better. So this is what our uniform distribution looks like. And maybe I'll draw some dotted lines straight down just to indicate that this is like a step function like that. So this is our PDF. If we have a vertical axis, this is just a straight line at height 1 over b minus a. What's the total area under this rectangle? Well, that's the base width, which is b minus a, times the height, which is 1 over b minus a. B minus a over b minus a is 1. So our total area is 1, as we had hoped. And we started on this example last time, got through a couple parts of it, and we're going to pick up here. So our example was, suppose that we know that a certain train, like subway, metro, bus, train, something like that, arrives every 15 minutes, but we don't know when it last arrived to the station. We just know it comes every 15 minutes. We don't know its schedule. We don't know when it was last here. So we choose to model the amount of time that we have to wait for the train to arrive, x, as a uniform random variable in 0 to 15. Right? We could have stepped onto the platform just as it pulled away, and we basically have to wait 15 full minutes for it to come back around. Or we could have stepped onto the platform just as it's about to come around the corner, or sometime in between. And we don't have any real reason to think that we should have, that we stepped on the platform closer to when it left or closer to when it's going to arrive or anything like that. So we'll model this as uniform. Really, the only piece of information that we have is that it comes by every 15 minutes. So we can, let me be a little smarter about how I do this time. I'm going to draw the distribution up here and then copy it as a picture down below so I can erase more easily without erasing the distribution. So we can draw our distribution. X is uniform on 0 to 15. So here is 0 and 15. We have height then of 1/15. 15 minus 0 is 15. So if our width is 15, we need to have a height of 1/15 to make a total area 1. And there's our PDF. So now let me see if I can do this. All right. So if I actually paste it down here as a picture, I'll be able to draw on it and then erase, and I won't have to try to erase just the pieces for each individual part. I can just erase over top of the picture. Okay, so we looked, for instance, at the question, well, what's the probability x less than 15? What's the probability we have to wait less than 15 minutes? Well, here we're looking at the event being to the left of 15. Now, we do kind of implicitly include some of this x-axis to the left of 0. But we do notice that the PDF is just 0 over there. This really isn't going to contribute anything. So really effectively what we're looking at is just what is the area under the curve between 0 and 15, and we don't really have to worry about this left tail over there. Or so I'm really looking for this area. What is this area? Well, it's the base width. It's a rectangle, so it's the base width, 15 minus 0, times the height, 1/15. It's just 100%. It's just the entire distribution. We know that under our model, the train comes every 15 minutes. We will never have to wait longer than 15 minutes. We will always wait less than 15 minutes. Again, the probability we wait exactly 15 minutes because it's a continuous random variable is 0. So we're not being really careful whether this is a strict inequality or non-strict. We see 100% chance. So we'll never have to wait more than 15 minutes. Now, again, like we had discussed a few times previously, you know, you might take umbrage with this a little bit. You might say, well, we know in real life trains might break down or something, right? And it might, uh, maybe we know the schedule is every 15 minutes, but something happens or the bus hits traffic or whatever. Well, sure, but that's a shortcoming of our model, right? That's a question of when we apply our model to the real world, what are the limitations of that application? But according to our model, we never have to wait more than 15 minutes. So we're still in this chapter 4, 5, 6, where everything is very theoretical, everything's very mathematical, everything's very precise. When we start trying to mesh these models with real world data is when we get back to something that feels more like statistics, where we say, well, most of the time we feel this way, or there's strong evidence in favor of this or that, but not necessarily. So that's kind of where we're headed for chapter 7 and 8. Somehow my probabilities down here got unitalicized. There we go. So what's the probability that x is between 3 and 5? Let me get rid of these. Good. So probability x is between 3 and 5. Well, maybe here is 3 and here is 5. And again, I'm looking for the area under the PDF between 3 and 5. This is a rectangle with base width 5 minus 3 or 2 and height 1/15. So that's 2 over 15 is this probability. And in fact, it's true of the uniform distribution, and it's actually a characterization of the uniform distribution that any 2-unit distance, whether it's 3 to 5 or 9 to 11 or 0 to 2 or whichever two unit width interval you pick, has the same probability. So the probability is only dependent on the interval width and nothing else. What's the probability x less than 5? So again, we got to be a little bit careful here because here's 5, and I'm looking at an event where I'm just to the left of 5. So something like -3 or -50 would fall within this event. But again, we know that those events less than 0 are impossible. So really, I only have to look at the interval from 0 to 5, kind of where our probability starts accumulating, and then go up to 5 where our event ends. What's this area? Well, again, it's a rectangle. It's a rectangle with base width 5 minus 0, and height 1/15. So we multiply the two, we get 5/15 or 1/3. So about 1/3 chance that we have to wait less than 5 minutes. And again, we could say the same for any other interval of width 5. What's probably we have to wait between 10 and 15 minutes, 1/3, or between 7 and 12 minutes, 1/3. What's the probability x is bigger than 10? Again, just as I just mentioned, this is similar to the last one, we don't have to worry about the bits of outcome that could be above 15 because they occur with probability 0. This is really just the probability is really just the area of the rectangle where the base is between 10 and 15, or the base has width 5, and the height is 1/15. So again, it's 5/15 or 1/3. Now, something we do want to be careful about, let's say it is kind of an aside over here. I can say maybe probability, what, 0 less than x less than 5 is, well, what would this be? 5 minus 0 over 15 minus 0. The 15 minus 0 is always there, and the 5 minus 0, there's the 5, and there's the 0. So I get 5/15 or 1/3. If I ask a question like, what's the probability that -5 less than x less than 5? What's the probability x is between -5 and 5? Even if we forget about the scenario here and we say, maybe I don't understand what it means to wait -5 minutes, but even if we forget about the scenario and just ask this in a purely mathematical sense, we might be tempted to write, well, I guess this is 5 minus -5 over 15 minus 0, just plugging in those two endpoints and get, well, 5 minus -5 is 5 plus 5 is 10 over 15, right? Is this correct? Well, let's think about, what if I said like probability -20 less than x less than 5? If we did the same thing here, 5 minus -20 over 15 minus 0, this would be 5 plus 20, it would be 25 over 15. What would this be, like 167%? Right, 25 is like 15 plus 10, so 15/15 is 1, or 100%, plus 10/15 is 2/3. How do I have a probability that's more than 100%? So again, I have to be really careful when I'm applying things like, algebraic rules. I have to be careful about when they apply. And if I look back at my picture, probability that x is between -5 and 5, I actually see on the interval -5 to 0, I really get no contribution to the probability. So really, I should think of this. I shouldn't think of it this way. I should think of it like probability uh, -5 less than x less than 0. So probability x is between -5 and 0, plus the probability x is between 0 and 5. Because I'm on two different pieces of the function in these two different places. And this probability x is between -5 and 0. Well, my base width is 5, but my height is 0 here. And then probability x is between 0 and 5. Well, we've done that one already. We saw that was 1/3. Right. So this shouldn't be 10/15, but it should be 1/3, the same as probability x is less than 5 over here. And same thing down here, from -20 all the way up to 0. Is on one part of the graph. It's on the part with height 0. And then for x between 0 and 5, that's on another part of the graph. Again, this should be 0 plus 1/3. So these really should all be the same number, 1/3. Essentially the same event as this one. So we do have to be a little bit careful when we're applying, just formulas, when those formulas apply, right? This 1 over b minus a bit only applies for x's between a and b. If we step outside of that interval, if we step outside of the interval 0 to 15, if we either go below 0 or above 15, we need to take care because we're on two different pieces of the function. And then we could ask a question like, what's the probability x bigger than 20? Well, of course, 20 is out here. And regardless of how wide that interval is, it has zero height. The PDF has zero height. So probability x bigger than 20 is simply zero. Okay, now let's talk about the expected value of x. So let me see if can I get just this? I think I can. Yeah. So let's take a look at what do we think the expected value is? Well, the expected value, remember, in the discrete world was the center of mass. So really what I'm thinking of here in this uniform distribution is that the mass is kind of like evenly smeared about this whole two-dimensional rectangle here. The mass is just kind of smeared about there. It's almost like we had an amount of mayonnaise or something and like, smeared it over that area. So it has uniform height for this rectangle. Where should the center of mass be? I think intuitively we would say if I said I have this like, block of metal or something that is 15 units wide and 1/15th unit high, where would it balance? We'd say probably right in the middle because it's a rectangle. It has a nice axis of symmetry there. So I might intuitively guess my expected value, my center of mass, is right here in the middle, 0 plus 15 over 2, or 7.5, as the expected value of x. And that would be correct. That is the expected value. It's because I have this nice axis of symmetry that if I flip the whole picture over this vertical line at 7.5, it looks exactly the same. That's my expected value. The expected value is actually the area under the function x times f of x, right? Again, if we look back to the discrete distribution definition, we summed up x's times probabilities. We summed up outcome times probability. And here we're kind of accumulating in the sense of generating an area. We're accumulating x times probability density. The main difference is we're not summing up because we have this kind of continuous smear of probability density. So if I look at x times f of x from say a to b, well, let's look at f of x from a to b first. So here's a to b. And let me do this in red. And that's at height 1 over b minus a. So this is f of x. And then let me look at on a to b, what does the graph of x times f of x look like, or x over a minus, or x over b minus a? Well, it starts at height a over b minus a and goes to height b over b minus a. So it's actually this function. It's a linear function. And actually, it's this area that we're interested in. We're looking for the area under x times f of x from a to b. This is actually a trapezoid, this area. What is the area of a trapezoid? Well, it is the base width one over b minus a times the average of the heights. So that's b over b minus a. plus A over B minus A over 2. You add them together, you divide by 2 to get the average of the heights. Or that's A plus B over 2. And then we have a 1 over B minus A uh, oh, I was going to say something went wrong there. I have a typo here. I got too excited about my 1 over B minus A's. This is just B minus A, the base width. And then so I have a plus B over 2. And then I have a 1 over B minus A factoring out of here, multiplied by the B minus A, not 1 over B minus A. I end up with B minus A over B minus A. They go away. So the expected value is just the middle of the interval. If I walk onto this train platform, how long on average do I expect to have to wait? 7.5 minutes, right? Sometimes it'll be less than that, sometimes more than that, but kind of on average, it'll be 7.5 minutes. Or if I do this 100 times and average the amount of time I had to wait each time, should end up close to 7.5. So my expected value for this particular distribution on 0 to 15 is 7.5 minutes. And the expected value for a general normal distribution on A to B, or a general uniform distribution, we got normal distribution on the mind because that's where we're going next. But the expected value for a general uniform distribution on A to B is the average of A and B, the average of the two extremes, the max and the min that we can achieve. And that I think is sensible. We would expect that. Okay. Any questions on the uniform distribution? So the super nice thing about the uniform distribution is that all of the sides under consideration are straight, so we can use basic geometry to find areas. Now, the unfortunate thing, I suppose, is that the uniform distribution in a small, proportion of cases is a great model, but we need more complicated models. In particular, we need the normal distribution. That's going to be the distribution that our central limit theorem is going to apply to. And that central limit theorem is really what's going to give rise to a lot of the inferential statistics that we're going to see in chapter 7 and 8, and even throughout the rest of the course. So it's either going to be normal distribution or variations on normal. That's going to be pretty much the kind of engine underlying most of the rest of the course. Okay, so what is the normal distribution? Well, it's the bell curve. If we remember all the way back to chapter 2, we talked about this bell-shaped distribution. It had some characteristics. It was symmetric about the mean. It had a peak in the middle, and it tailed off to both sides. It looked like this. Right. Had a peak in the middle. It was symmetric about that peak, and it tails off to both sides. Now, an unfortunate thing about the normal distribution is this is what its probability density looks like. That's not a very nice looking probability density. It's not just like a constant. Roughly speaking, it looks like e to the negative x squared. So this looks kind of like e to the power negative x squared. This tells us maybe a couple of things. Well, one thing is we do have some nice symmetry. The only place that we see an x coming in, it's getting squared. In this case over here, it looks like x minus mu squared. So x minus something squared, but that's basically an even function. It looks the same if you flip it over left to right. And this symmetry means that the mean, the median, and the mode are all equal, so it doesn't have any skewedness. So that's kind of a nice thing to know. It's defined for all real numbers, this can maybe in some senses be a nice thing. We don't have to worry about all these kind of special cases that we had to think about up here, right? Being careful that we exclude some certain parts of our outcomes and so on, or treat them, separately. But we might ask then, well, what if I wanted to model something like a person's height by a normal distribution? If it's defined for all real numbers, and maybe I should even say not just defined, but it's non-zero, it's positive, strictly positive for all real numbers. That means, somewhere I have like 0 feet, and the normal distribution is saying that, there's some positive probability that a person is between -2 feet tall and -1 feet tall. That doesn't make any sense. Or there's some probability that a person is between 20 and 21 feet tall. Some positive probability. That also doesn't really seem to fit with reality. Now, again, our kind of motto for the course is all models are wrong, some are useful. So the normal distribution in and of itself is just really a probability concept. But if we try to overlay it to model something, allowing it to be defined for all real numbers or positive for all real numbers can end up giving us some kind of contradictions like this, that there's some positive probability that somebody is between -5 and -3 feet tall or something like that. But the thing is that these tails, they go to zero extremely fast. So how fast can something go to zero? Like 1/x kind of goes to zero as x gets big, but it goes pretty slow. Something like 1/x squared goes a bit faster. Something like 1/e to the x actually goes pretty darn fast, exponentially fast. That's quite fast. Something like 1/e to the x squared, this goes to zero extremely fast. If I put in x even like 3 or 4, we're already pretty darn close to zero. So in practice, if I was modeling heights with normal distributions, okay, maybe my model says that there's some positive probability that somebody is between like -10 and -5 feet tall, but that probability is going to be like 10 to the -30 or something. It's going to be such an incredibly small number that we can effectively ignore it. It's not going to have any meaningful effect on what we estimate to be the mean of the population heights, or what we estimate to be the likelihood that somebody is, say, close to 6 feet tall, or anything that we would want to query this model for to use in real life. It's not going to be affected by this little strange paradox or whatever it might be over here, or the same thing over here. So as long as we're not too rigid in our thought process when we're applying these models to the real world, as long as we accept that the model is wrong, but it may well be useful, and we understand its limitations and its strengths, then I think we're in the clear. So in practice, these tails get small enough, fast enough that modeling things with the normal distribution usually isn't too terrible of a problem. There are some areas like finance, for instance, where these tails getting very small, very fast actually is problematic, because you think of like the stock market, most of the time, maybe 95 or more percent of the time, it's just kind of going along doing its thing. It's pretty calm and reasonable, and just kind of grows a little bit, little bit by little bit. But then every once in a while, a couple percent of the time, it's doing something crazy. It's like it's a big crash or something like that, or a big recovery or something along those lines, something very much out of the ordinary. And those things happen more often than would be predicted by a normal distribution. So, the things like way out here in the stock market actually do happen quite often. So we wouldn't want to model those with normal distribution, because normal distribution is saying things way out here almost never happen. But if I was modeling, say, people's heights, things way out here actually almost never happen, and the normal distribution says they almost never happen. Yeah, so that's concordant. I might be happier modeling something like heights with normal distribution. We have one more unfortunate thing about the normal distribution, and that's that, remember, probabilities are represented by areas. I can figure out if I'm given a certain value for mu and a certain value for sigma. This pi is just the normal pi, like 3.14 and so on. But mu and sigma are parameters, kind of like the A and B up here, right? Just like in the uniform distribution, having it identified on A to B means that I can adapt this model to a scenario, right? If I had a different train that came every 20 minutes, I could use a model that's uniform on 0 to 20. So I have parameters that I can choose. I have parameters I can choose down here for the normal distribution as well, and they are mu and sigma. As you can probably guess, the mean or the expected value and the standard deviation of the distribution. So I can choose those. But once I choose those, I could type this into my calculator. It might, be a bit of a pain to type in the calculator, but I could. It would give me a number. So I could actually ask my calculator to graph this graph for me, or I could ask it for this X input, what height is associated with it. I can get answers like this pretty easily. I mean, at least conceptually speaking, it might take a bunch of button presses and be kind of annoying to type in, but conceptually pretty easily I can get answers like this from the calculator. But remember that it's usually not the output of the PDF of the function that we're interested in. We're usually interested in probabilities, which are areas. So really, this isn't what I'm interested in so much. What is the height of the function at a certain input? What I'm interested in is between two boundaries, what's the area under this curve? Now, when it was a straight line, that was an easy enough question. I was just looking at a rectangle, and I know how to compute the area of a rectangle, base width times height, multiply the two together, you get the answer. But this is very much not a rectangle. It's not a rectangle, a triangle, it's not a circle, it's not a basic geometric shape, it's its own shape. So I don't really have a good way to compute areas under this more complicated curve. And that's where my standard normal table comes in that I posted to chat. Let me post it again just in case anybody popped in a couple minutes late. So I just posted it a second time. The standard normal table is in chat, so you can download that as a PDF and kind of follow along. Also in the book, it'll also be up on Blackboard. And I do recommend using this one that I posted or the one that's in our book. This is the same as the one that's in our book. Because if you Google standard normal table, you'll get tables with the same information, but often presented in slightly different ways, and it can really kind of trip you up if you're not exactly sure what you're looking at. So I'd recommend using the same one all the time. Okay, so probabilities are represented by area. So the first challenge that we have to overcome is how do we find areas under this curve that is pretty complicated? I could evaluate the curve at certain inputs, but getting an area, I'm not so sure about that. That's what our table is going to help us with. Let's work to conceptually understand this a little better first. So this function, as an aside, if you are taking Calc 1 or have taken Calc 1, try to kind of prove what I'm going to say about this, that this function, how mu and sigma affect the graph of the function. So let's say that I start with a normal distribution that looks like this. For this distribution, well, remember we said that because it's symmetric, that was one of its defining characteristics, then the mean and the median and also the mode, the most frequently occurring value, are the same. So the mean is really just at the peak, that point of symmetry. So mu is the location of the peak. And then sigma is sigma helps us locate the inflection point. What's an inflection point? Well, we might notice that this curve kind of has three pieces in a sense. It has a piece where it's kind of concave down, where it's kind of like curved down. It has a piece over here where it's kind of more curved up, and a piece over here where it's more curved up. Where we go from curving up to curving down, or vice versa, we call that an inflection point. And those are, say, more or less right here and right there. These inflection points where we change from curving up to curving down or vice versa are one standard deviation away from the mean. So this distance is sigma, this is sigma, and this point on the x-axis is mu minus sigma, and this point mu plus sigma. So we call mu a location parameter because if I'm going to use kind of the same axis copied down here. Well, if I change mu, you see, can I select this curve? I've been having really good luck copying and pasting on OneNote these days. I feel like I should play the Powerball or something. So if mu increases, I get exactly the same curve back if I increase mu, but it's just shifted to the right. So if mu goes up and sigma stays the same, so mu increases, standard deviation stays the same, my curve just shifts over to the right. But it looks exactly the same. The shape is the same, but the location is different. Or likewise, if mu decreased, then my whole shape would stay the same, but it would just shift left. So mu is my location parameter. It tells me the location of that peak of the mean of the distribution. Sigma, on the other hand, is a shape parameter. So here, if mu stays the same, I'm going to try to keep everything more or less nicely lined up here. And if this was my previous distribution, like up here with that initial sigma, what if sigma increases? Well, then what's going to happen is this distance here from the center to the inflection point where it changes curvature, if sigma increases, that's going to get wider, that distance. In other words, that's going to kind of want to push the curve out like this. But now if I just did that, I actually notice if I just did that, if I just pushed the curve wider and kept it kind of the same height at the peak, well, now I've actually like added more area like here and here under the curve that wasn't under there before. The area used to be 1, but now the area's got to be more than 1, right? Because I made it wider and it stayed the same height at the middle. I've added more area in. So actually, in fact, I do make the curve wider, but it also kind of gets squatter. Right? So now my sigma has increased. Before it was only representing this width out to this inflection point for the dotted black curve. Dotted black curve. But now it is stretching the curve out horizontally, but that also means it has to be squatter. So I'm kind of like adding in some extra area here, but I'm getting rid of some extra area from the peak. So those are balancing out. So this is an example where sigma increases, but the mean stays the same. Or I could have sigma decrease. If sigma decreases, that means that my peak is getting kind of narrower, right? The distance out to the inflection points is getting smaller. So my distribution is getting more squeezed in towards mu. And of course, if I just squeeze it in towards mu and keep it the same height, now I have too little area because I've lost some area off of the sides of the peak there. So I've got to compensate by making it taller as well. So this would be sigma decreasing, mu staying the same. So sigma is our shape parameter. Shape parameter, or maybe scale parameter, something like that. If I change sigma and don't change mu, the location of the middle of the distribution stays the same, but it gets broader or thinner. And in fact, these kind of small sigma uh, normal distributions where sigma is less than 1, we call these leptokurtic, kortos meaning humped in Greek, and lepto meaning something like thin, so like thin hump, versus platykurtic, like platypus, broad foot, well, platykurtic, broad humped, for sigma bigger than 1. So sigma is our shape parameter. It makes the distribution wider and shorter, or skinnier and more pointy. And that kind of makes sense because if sigma is small, if my standard deviation and variance are small, most of the outcomes that I observe should be pretty close to the mean, right? And most of the area in this red curve, most of the area under the red curve is pretty close to mu. Whereas if the variance and the standard deviation were large, it should be reasonably likely that I get outcomes far away from the mean. And if I look at the area under the green curve, a good bit of that area is kind of far away from mu. So that also makes sense. Okay, so those are the effects of changing mu and sigma. Mu is our location parameter. Changing mu just shifts our picture left to right. And changing sigma changes the shape of the picture, makes it either broader and squatter or narrower and pointier and taller. Okay, so now let's take a look at the standard normal table. And as I mentioned here, the table is on will be on Blackboard. It is in the chat, in the Zoom chat, and it's also in your book. So the first thing we need to discuss is, well, I have actually a family of distributions, a family of functions here. I can pick mu any way I want. It can be any real number, and I can pick sigma to be any positive real number. So how can I really say anything about this distribution? Well, there is a standard normal distribution. There is kind of a member of this family of normal distributions, a certain choice of mu and sigma, that's kind of the default in some loose manner of speaking. So the standard normal, we use for the standard normal, we use the essentially trademarked letter Z to represent the standard normal distribution. Pretty much everywhere in probability and stats, if you see Z, it has some reference to the normal distribution. You might be thinking to yourself, hey, wait, didn't we talk about a Z-score in chapter 3? Yeah, that's inherently tied to the normal distribution, as we'll see a little bit later. But Z is a normal distribution where the mean is 0. That's a nice place to kind of center a distribution. And the standard deviation is 1. The parameters for a normal distribution are often listed as mu and sigma squared, the variance, but for ease of understanding, I'm going to list it as mu and sigma when we're in this class. And we kind of see that that's the leptokurtic and platykurtic situations are when sigma is different than 1. That's when we're, more broad or more narrow than the standard normal. And what does the picture look like? What does the PDF look like? Same shape, roughly speaking, as any normal distribution, but it has a mean of 0. This inflection point is at +1, that inflection point at -1. And our intuition should say, I mean, I didn't draw this super carefully, but it should say that like the chance that we end up between -1 and 1, that looks like a lot of area. That should be like most of the time, maybe a majority of the time. But we do have a decent chunk of area outside of -1 to 1. But if I go twice that distance to say -2 to 2, well, now I'm taking up almost all the area. I almost always should be between -2 and 2 in a standard normal. So this is Z, our standard normal. So let's start working through some of these probability questions. I have several different examples here. These will take quite a while to get through. So even though it looks like a very condensed situation here, it's going to take us definitely the rest of this class and probably a good bit of the beginning of next class to get through this. Okay, let me switch up my share here. I'm going to get my normal table opened up and kind of sized up appropriately, and then switch my share in just a second here. I think that will work pretty well. Okay, so let's look at this question about a probability. Let's try to answer it. We actually might be able to answer this one without looking at the table. And then let's refer over to this table. And I know this is really small on your screen. I'm going to be doing things like highlighting to help you kind of see a little better, but I do recommend that you follow along on your screen uh, with the PDF I posted in chat. So that's going to be a lot easier for you to see if you're kind of seeing what I'm doing and then I'm referencing it on your screen. I mean, unfortunately, I can't zoom in too far on this. If I zoom in far enough that it makes the numbers big enough, it's really hard to tell where we're actually at on the table. So, you know, that's about, that's close to the best I can do, or I think I can go one more. There we go. Okay. So let's try to answer the question, what's the probability that Z is less than 0? Our standard normal distribution, the normal with mean 0, standard deviation 1. Well, I can draw a picture. There's Z. Since this is my standard normal, I know that the mean of 0 is right at that peak. So that peak is located at 0. And remember, I know that I'm symmetric about the mean. That's true with any normal distribution, standard or otherwise. I'm looking for a probability, so I'm asking for the size of an area. What area is that? Well, that's the area to the left of 0. Well, here's 0, and I'm looking for the area to the left. And actually what I notice is by the symmetry, the area to the left of 0 has to be the same as the area to the right of 0, right? Because if I flip this whole thing over, that area to the left of 0 just becomes the area to the right of 0. But I also noticed that the sum of their two areas these are mutually exclusive areas. I can just combine them together. That's probability Z less than 0 or Z greater than 0. Well, that's essentially the probability minus infinity less than Z less than infinity. The probability that Z is somewhere on the real line, which is 1. It's the total area under the PDF or 1. So the sum of these two has to be 1, and they have to equal one another. If I'm adding up two things that are equal to one another, I have to add to 1. It has to be 1/2. And you might have even been able to get there faster, just kind of using intuition and gut feeling and so on. So there are actually 3 probabilities I can find on the standard normal distribution, or for that matter, any normal distribution. I can find probability z less than 0 as 1/2. Probability z bigger than 0 is also 1/2. And probability that minus infinity less than z less than infinity is 1. Now, unfortunately, no matter how good you are at math, there are no other probabilities. There are no other events where you can find the probabilities in a nice closed form, exact answer like this. When I say this probability is 1/2, I mean exactly 1/2, not approximately. Every other one of these probabilities, we're going to get an approximate answer to. And it's not a question of, well, you just don't know enough math to get an exact answer. No, it doesn't matter how much math you know, you're going to be stuck with an approximate answer no matter what. Okay, so if I'm looking for, I want to use the table to find this as well. So how do I use the table to find these probabilities? Well, I come over here to my table and I notice that there are, let me zoom out one more. I think I zoomed in just a little too close. Okay. Trying to find the zoom option here. Um, yeah, I think I want like 105. I'm trying to make it as big as I can for you, and but still actually be able to see all of the information on the table. There we go. So that's about the best I can do, 105. So if we look at this PDF, there's actually 2 pages to it. There's a first page that says negative z-scores at the top. It has kind of this kind of picture here where the smaller area is shaded in. Or there's the positive z-scores page that has a larger area shaded in. And I noticed that what this table is giving me is cumulative area from the left, or I would probably say to the left. I noticed that there are an index, column, and row. I see there's a little z. Sorry for the flashing, but whenever I click on the PDF to undo the selection, it selects the whole thing. So I see that there's a little z here up in the very top corner. Below the z is an index column. So 0, 0.0, 0, 0.1, 0, 0.2. And then beside the z is an index row, 0.00, 0.01, 0.02. So if I'm looking for the probability z less than 0, really that is probability z is less than or to the left of 0.00. So 0 units and 0 tenths, and also 0 hundredths. So I'm interested in the z index, 0.0, getting me to the tenths place accuracy, and 0 hundredths as well. So I'm interested in this row corresponding to 0.0 or 0 tenths, and also this column corresponding to 0 hundredths. At the intersection of that row and column, I see that there's a number, and now I think I can zoom in so you can see a little better. 0.5000. That is our 1/2 or 50%. 0.5. So our table gives us areas to the left of some z index. Our table gives us area to the left of some z index. The z indices, these z numbers on the horizontal axis here, are what are identified in the index column and row. And in kind of the middle of the table, or I often call it the field of the table, in the middle here, these are all areas or probabilities. Right? So we have z indices, and we have areas or probabilities. And our table gives us an index column and row. And then in the middle, in the field of the table, we have areas or probabilities, areas to the left in particular. Maybe I should shade the rest of this in to the left. So we're going to get quite a bit of practice using this table. It's a bit strange to use the first, 2 or 3 times that you use it. The next 2, 3, 4 times you use it, you're kind of starting to get the hang of it. And again, as with so many things in math, by the time that you've done 10 or 15 or 20 repetitions of practice, it's quite a bit more natural to use. I also like the way that this table from our book is constructed. It makes it really easy to know what's what and to find the answer you're looking for. There are a lot of tables that will give you the area from 0 to z, and then you need to figure out, like, okay, if I want a left tail area, I have to add 50% to that because it's not incorporating, right? There's lots of ways that they write these tables. So that's why I recommend using the one that we're using here. That's the one from the book. I think this really is the best way to present the table. All right, let's look at the probability that z is less than 1. So again, I'm going to draw out my picture. Even when you get really used to these problems, I think it's worth taking the extra 15, 20 seconds to draw out the picture and label everything just to make sure that, well, number one, so that your intuition of what the answer should be based on the picture matches what you actually got. That's kind of a nice way to check that essentially the geometry matches the algebra in a sense. And also we're going to see as we get down here to more complicated problems, having a picture is going to really help us to figure out exactly what numbers we need from this table. So here's my standard normal distribution, and I'm interested in the area to the left of 1, right at this inflection point here, that's 1. And I want the area to the left of that. Or really, this is probability z is less than 1.00. Now I look over at my table. The first thing I want to ask is, well, what sheet should I be on? Oh, you can see my desktop is a bit of a mess. The first thing I ask is, what sheet should I be on? I have the positive z-scores that has a picture that looks like this, and the negative that has a picture that looks like that. Well, the negative z-scores picture doesn't really look as much like the picture I have over here, where my area kind of fills up to 0 and then keeps going. This is an area that stays strictly to the left of 0. My positive z-scores side matches better. This area fills up to 0 and then keeps going. In fact, I can I can see that it's got to be bigger than 50% for my answer. The area to the left of 0 is 50%, and then this has some extra between 0 and 1 here. So I know my answer should be bigger than 50%. I'm expecting an answer bigger than 0.5. I also noticed that on my negative z-score side, all of my probabilities or areas are less than 0.5. And on the positive z-score side, all my probabilities or areas are bigger than 0.5. So it makes sense, again, to use the positive z-score side. The picture looks more like what I expect. And also the probabilities that I'm going to get out mesh with what I expect the answer to be. So I'm looking for the area to the left of 1.00. Well, that is 1.0 accurate to the 10th place, and then also 0 hundredths. So I look down my z-index column. I went 1.0 tenths, or 1.0 accurate to the 10th place. So I want to be in this row, the 1.0 row. And then I want 0 hundredths added on. I'm not looking for the area to the left of 1.03, where I might pick this row and column intersection. No, I'm looking for the area to the left of 1.00. And I see that intersection is right here at this 0.8413. Or that's 84.13%. Does that make sense? Is it bigger than 50%? Yep, that's what I was expecting. And it looks plausible. I mean, just kind of at a glance, I didn't take great care to draw this picture very, very nicely, but it does seem like we should have a decent chunk of area that's not accounted for. If I got an answer like 99.9%, I'd be a little suspicious, right? But 84%, yeah, there's a decent chunk of area there that's not accounted for, and it's a larger area than 50%. Going up to 0 and stopping would be 50%. I went a little further than that. This seems reasonable. What about probability z less than -2? So there's 0. This is a picture of z. At the inflection point here, to the left is -1. That's 1 standard deviation below the mean, or remember, we're on the standard normal where the standard deviation is just 1. And then I have to go that distance again to go to -2. What's the probability z is less than -2? Very clearly, this is going to be less than 50%, but actually probably a lot less than. So I'll put like 2 less than symbols there. This should be quite a small number. It's not going to be like 48% or probably not even like 35%. It's going to be a lot smaller than that. Now, if I look at this picture where, there's a lot of the area unshaded and just this left tail is shaded in, that doesn't mesh with the positive z-scores picture. The areas that I'm looking for, or the area that I'm looking for is going to be way smaller than 50%, not bigger than 50%. And my z-index is not positive like these over here. It's going to be like -2.00. So I actually have to come to the other sheet with the negative z-scores. This does have areas that are quite small. That's what I'm looking for. The picture meshes better. And I see my z-index column has negative numbers. So I'm looking for things around -3.0 or -2.0 or something like that. That's exactly what I'm looking for. I want to be on the negative z-score side here. Again, I note that this is the probability z less than -2.00. So accurate to the 10th place is -2.0, and then 0 hundredths. So I want to come over to my z-index column. I'm looking for negative 2.0, so I know that my answer is going to be somewhere in this row, 0.0228, 0.0222, something like that. And I want 0 hundredths to go along with that, so I'm going to pick the z-index column with 0 hundredths, this leftmost column. This is the only one we've used so far, but we'll deviate in just a minute here. So negative 2.00 for the z-index has an area to the left. It's associated with a probability 0.0228. That is indeed a number much less than 50%, like we expected. This should have been quite a small number, is what we expected, and it is. Right, being 2 standard deviations below the mean is kind of an unlikely thing to happen. Okay. One note that I mentioned earlier is this 1/2, this 1/2, and this 1 are exact. Everything else is approximate. And sometimes I make a point of saying that this is an actual equals because these two things mean exactly the same thing. And this is really an approximately equals. This 0.8413, if I were to do more calculation or find a table that had more decimal places of accuracy, it's probably 0.8413 something, right? It's going to be 0.8413, whatever, 476 or something like that. And it's going to keep going. So essentially, from this point on in the course, more or less every answer we give is going to be approximate. So because I don't want to write squiggly equals 10,000 times, I'm going to write equals, but the understanding here is that pretty much everything in the course from this point out is approximate. So just a little side note on that these are approximate answers that we're getting here. And one reason I mentioned that is probably next time we'll look at computing some of these probabilities in Excel, using it to help us compute these. It might give a very slightly different answer than what we see here. If we round it to 4 decimal places, it should be the same answer. But Excel might report, 5 or 6 or 7 decimal places. Don't get thrown off by that. These are approximations. Okay, what is probability z less than 0.347? So again, I look at my standard normal curve. There's my standard normal PDF, centered at 0. This inflection point at +1, 0.347 is in between these two. I'm looking for the area to the left of that when z is less than that number. And I see that this includes all the area to the left of 0 plus a bit extra. Well, that means that my answer should be bigger than 50%, but not a ton bigger, right? I wouldn't expect 80 or 90%. I have quite a bit of area here that's left out. Maybe 55, 60, 65%. They might be reasonable numbers, but not something like 90%, and certainly not an answer less than 50%. Now, I see that probability z less than less than 0.347. The z indices in my table allow me to be accurate to the 10ths place and then to the 100ths place, but really no further. This is in the thousandths place. I'm going to round. I'm going to say this is approximately probability z is less than 0.35. So I'll start off by just, if I need to, rounding my z index to 2 decimal points, 2 decimal places. And now I see accurate to the 10th place is 0.3, and then the 100th place is 0.05. Now, which side of the table do I need to be on? Well, the negative z-scores picture doesn't line up here. We're expecting an answer bigger than 50%. We have a positive z-index. We're on the wrong side of the table. Let's go to the other side. We have a positive z-index, like positive 0.35. The picture meshes more with the picture that I have over here. Looks a little closer. And the probabilities, the areas that I'm going to get out from the field of the table, are above 50%, which is what I'm expecting. So this is the side of the table I need to use. Right? That's always the first thing we need to figure out. It's a little easy if you're going quickly to use the wrong side of the table and maybe not realize that this negative sign is there, right? So the negative sign should give you a clue, but it is a little easy if you're going quickly to miss that negative. Okay, so I'm on the positive z-score side. I'm looking for a z-index of 0.35, which means I want to go in the first column here to 0.3. So the answer that I'm looking for is going to be in the 0.3 row. And now I need 5 hundredths. So I'm not using the leftmost column in the field anymore, the 0 hundredths column. I'm using the 5 hundredths column. And I see the intersection of this 0.3 row with the 0.05 column. That picks out this number. It is 0.6368. So again, we're expecting a number bigger than 50%. That's what we got, but not like a ton bigger. We weren't expecting like 80 or 90%. We didn't get that either. So this is in the ballpark that we would think is reasonable. Any questions so far? Okay, and we have one more that is kind of like these ones. Probability z less than negative 1.223. So I'll start by drawing out my z distribution centered at 0. I know this inflection point here is at -1, and I'm a bit to the left of that at negative 1.223. And I want an area to the left of negative 1.223, so that is this area here. I know this should be certainly less than 50%, and should probably be quite a bit less than 50%. I don't think it should be like, it's probably not less than 10%, probably not like 2% or 5%. Doesn't look quite as extreme as like this one up here, probably z less than -2. But it shouldn't be like, 45% or something like that. We're missing an awful lot of the area, even on the left side here, of that full 50%. Now, again, I have 1.223. I have information all the way up to the thousandth place. But my table only allows me to be accurate to z indices out to the hundredths place. Yeah, so I got around this. So I round to the hundredths place, and there I go, looking for probability z less than negative 1.22. And if I break this up, that's like negative 1.2 accurate to the tenths place, and then 2 hundredths. Now, again, I look at what side of the table I'm on, and the picture doesn't really match. Positive z-score, I'm looking for a negative z-score, negative 1.22. And the areas in the middle here are above 50%. I'm looking for ones below 50%. I got to be on the other side, on the negative z-score side. Here I do have a negative z-index. I see my z-indices are negative. That meshes with negative 1.22 better. My picture looks better. The probabilities I'm going to be getting out are more in line with being a lot smaller than 50%. This is the side I want to be on. So this is always the first thing we got to do, is decide which of the two sides of the table we're on, positive or negative z-score. And now I look at the area to the left of negative 1.22. Well, that is negative 1.2 accurate to the 10th place. So I'm looking for an answer in this row, the negative 1.2 row. And then 200ths. So I'm looking for an answer in the 200ths column here. And I see that the one at the intersection is 0.1112. Or 11.12%. That is a number that's quite a bit less than 50%. Again, I wasn't expecting a number like, 2% or something like up here. It doesn't seem to be quite as far off in the tail as that. But this is a number that's quite a bit less than 50%. That's what I was expecting. Any questions so far? There is one more thing I want to point out that I actually forgot to mention up here in the probability Z less than 0.347. One thing we have to be we have to be aware of sometimes in something like this 0.347, right? If I just look at the number 0.347, kind of looks like a probability. But in this case, it's actually a Z index. It's actually a location on this horizontal axis. The probabilities are areas. I could, very well have a probability or an area that has area 0.347, right? So I have to, especially when I'm dealing with numbers that are Z indices between 0 and 1, I just have to make sure that I'm being especially aware of what is an index and what is a probability. What is a number that is on this horizontal line here indicating where we're at on that line, and what's a number that's indicating area under the curve or probability. It's just a little easier to get it mixed up, right? So when I'm looking for probability Z less than 0.35, I'm careful to realize that this is an index. So I'm looking for 0.3 in this row and then 0.05 for that column. It's kind of a side note. It might seem like a silly thing to try to keep in mind now, but when we get down here, we'll be looking at inverse operations. So looking at trying to find a probability and then figure out, for this probability, say 0.9099, like what Z index is that associated with? So later on, we're going to be looking at going the other direction. So it will be, more important to keep track of what numbers are probabilities, what numbers are indices, and keep that straight, especially whenever we have indices that look like they could be probabilities that are numbers between 0 and 1. Just a little bit easier to get that mixed up. Okay, let's take a look at least one or two of these next group. So take probability Z bigger than -1. Now this is kind of in a sense a fundamentally different problem than the one before. So here I have Z centered at 0. Here's -1, my inflection point, and that's the point of interest. But now I'm looking for an area to the right. I'm asking when is my random variable, the thing that I'm measuring, bigger than -1? I'm in that event, or I want to accumulate probability to the right. So note that this area is to the right, where the previous areas were to the left. I need to pay attention to the direction of the inequality. Whether it's strict or non-strict is irrelevant in these continuous distribution, but the direction means, switching the direction means a very different thing. So we have to pay attention to the direction. Now I have kind of an unfortunate occurrence here. My table, which was so nice to use for the last few problems, isn't really directly set up to give me this answer. My table gives me, if I can select it here, it gives me areas to the left, but I want an area to the right. So I have an issue here. I suppose I could carry around more tables, ones that have areas to the right, but that's kind of redundant. That's a bunch of extra tables. Can we use the area to the left information to figure out areas to the right? And the answer is yes. We can really do anything we need to do with just these two tables, with just the positive and negative z-scores, areas to the left. How do we achieve that? How do we use the information we have in the table to answer this question that's not directly related to the table? I can't just pluck a number off the table and be done with it. I got to do something else. And there are two methods. So one method, and I think it is really valuable to know both of these. Often when maybe there are two ways to answer a question, you kind of pick the one that you like the most and go with that one. I really think it's worth learning both of these methods. If you're struggling, maybe at the beginning, focus on one of the two methods, the one that makes the most sense to you. But you should make a concerted effort to, once you master that one method, also pick up the second method. And these aren't in any particular order, just the order that I'm thinking about them right now. One is the complementary event method. In other words, I can imagine constructing this area to the right of -1. I can imagine constructing this by looking at, say, the total area under the curve. Maybe I'll just draw that area in black. And subtracting off, well, if I have all of the area and I want to get the blue area left over, this includes all of the area that I want, but also some area that I don't want. I need to get rid of the area to the left of -1. And these are all z. These are all centered at 0. But I want to get rid of the area to the left of -1. So if I take all of the area under the curve, and then I subtract off the area that's to the left of -1, I get rid of that area. That should give me what's left over should be the area to the right of -1. Or algebraically, we would say something like the probability that z is bigger than -1 equals, well, the whole area under the curve, we had a requirement to be a PDF was that has to be 1 minus probability z less than -1. We really just see our complementary event rule from back in, what was it, chapter 4 popping up here, right? Probability of an event is 1 minus probability of its complement, and clearly z can be bigger than -1 or less than -1. Those are complementary events. Again, we're in the continuous world, so we're not worried about z equals -1. We would be very worried about that in, say, chapter 4 or 5, but not here. And nicely enough, so this area I just know it's 1, and this area is an area to the left that I can figure out with the table. I can reframe my area to the right as 1 minus an area to the left, and then get my area to the left using the table. Now I look at this and I note that I expect my answer to be bigger than 50%, not by a ton, but by a decent bit. So this is going to be 1 minus, and what's probability z less than -1? That's a negative z-score, right? This picture over here to the right looks like this picture. And I'm looking for a z-score of -1.00. So here's my -1.0 row. And then my 0.00 column is my leftmost column in the field. I see that's 0.1587. Now, why do I say to be so careful about writing out your picture, coming up with an estimate of the size of your answer, and so on? Well, the answer is because it's really easy to grab 0.1587 and say, oh, that's my answer, and enter it in my stat lab. Right? We did all of this work to get these pictures and all that. We looked everything up on the table. That's a lot of work. We might have forgotten about the 1 minus. But if I check, is 1.587, is 0.1587, that 15 or so percent, is that bigger than 50%? No, it's not. So I clearly, if I grab this, thought 15.87 is my answer. I check and I say, okay, it's not bigger than 50%. What did I forget? Oh, I forgot my 1 minus. So I need to do this one more step. 1 minus 0.1587 is 0.8413 or 84.13%. That actually does mesh with my initial expectation now. I'm much more happy with this answer, right? So one option is complementary event, and the second option, which I'll write down and we will work through next time, is using symmetry. And the idea here is to make use of the symmetry about 0. That if I want an area to the right of -1, I can flip the entire picture about 0 and make that an area to the left of +1. You might see that right away. If you don't see that right away, that's perfectly okay. So here my -1 flips over to +1. So probability z less than, or z bigger than -1 is probability z less than +1. And from here, I can look up on the table. So we'll talk about this in more detail next time, but just to give you kind of a heads up to what's coming, this would be the other way that we can approach a problem like this. We can use the symmetry of the distribution to turn a right tail area into a left tail area by flipping it around. Okay, let me end the recording.